into the wafer is also increasing with time. Which you to get the total amount, you just take the area of this curve. The area will give you the total amount. So that you can see is increasing with time. So that means since it's an infinite source, if we keep if we keep the process running, ultimately the ultimately we will the whole wafer will be the whole wafer will we will have the will have the dopants.
Sir, I was asking like what are the parameters doping depends on? Like what the dopant should have so as to diffuse maximum into the as wafer, or else what wafer should have so as it can receive more dopants.
So the wafer we are is basically it's basically silicon wafer. So but there is also an initial concentration of see this is a silicon wafer. So it's already doped P type or N type that we saw last class. It is doped during the growth it is doped when
Sir, I am asking like solubility. Like if
yes so
the wafer has more solubility, it can take more dopants.
yes so, no, so
And if the dopant size are small, then the diffusion will be faster. So I get more and more dopants. And if vacancies are there on in the material, will that be helpful for the diffusion process?
so vacancy is not I don't think but yeah vacancies will help you because so diffusion basically you want to replace the silicon in the lattice with your diffuse with your dopant atom. So yes, so like we saw like for negative doping, N-type doping, we can use phosphorus or arsenic or antimony. So as you see, phosphorus has a much smaller atom than arsenic. Arsenic has a much smaller atom than antimony. So if you diffuse them, you will see that phosphorus diffuses much easier. So yes, dopant the, the dopant size matter will smaller dopants are much will diffuse much easier. Also, the initial doping of the wafer is so whatever dopant you are introducing, it has to replace the initial doping also. So the amount of depth that you get will depend on the initial doping also. So if the initial doping like it's a N-type doping, already an N-type dopant, and you are introducing a P-type dopant, so the P-type dopant has to first replace the N-type dopant. So the
I understood, like substitutional, you are telling.
yes, so do
But vacancies don't contribute in anything.
so vacancies are not really a part of the lattice.
You are telling that if I take a wafer, it will not be having any vacancies.
It will have vacancies. Vacancies are Im- impurities. There, so vacancies don't vacancies will interfere with so you don't want any vacancies. So vacancies are impurities, they are not controllable. But the lattice atoms, the substituted atoms, they are controlled.
But sir, in a video, he tells like arsenic and antimony will predominantly do vacancy diffusion. If vacancies are available, they will go and diffuse there.
Yes, so see, uh, they will sit in the vacancies, but vacancies are contributing. Obviously, they are contributing. If they didn't contribute, we won't care about vacancies. right? Vacancies are contributing, but we prefer to have substitution. That is what I'm saying.
Like substitution will create another problem, na sir. If like it will create lattice mismatch. That is once again is not appreciable. It will create a strains and then the wafer will crack.
No, but you look your diffusion, your dopant amount is very small compared to your silicon. The doping concentration is very less.
Okay, sir. So it might not do go to that level of
Yeah,
extent.
you're not replacing 50% of your silicon atoms with boron.
Okay, okay. And in one place, sir told like when you grow the oxide layer
Yes.
onto the surface, there we see an n-type dopant, higher amount of n-type dopant at the interface, and lead and the p-type dopants are decreased below the interface, and at the interface n-type dopants are higher. Like how I can't imagine that how it
In case of oxide growth,
is likely. The presence of oxide layer on the surface of the silicon wafer during the drive-in of the dopants
okay.
can lead to, like he has given in the video, that increase in n-type dopant just below the interface. He has told that. But how it is, like what it actually is, I didn't understand.
So so that that will change due to so your SiO2 is blocking some amount of SiO2 is blocked. That is mainly dependent in your ion implantation method. So your SiO2 is blocking some. So your when the ions are entering into your wafer, they are losing energy as they travel through your wafer, right? So
Yes.
so if an SiO2 is present, they will start they will have to first cross SiO2 to reach the wafer. So during when they travel through SiO2, they are losing energy. So they
Like how they will travel through SiO2, sir? We will create a window. In that window, we will implant the ions and they will diffuse throughout the material. But here, like in one of his lectures, sir told like when you do that during the drive-in process of the dopants, he told that in the at the surface, or you can say just at the interface, we'll see more of n-type dopants, and when you go deeper, then like he told that at the surface you have more n-type than p-type. I didn't understand why.
no so the first step in fabrication process is oxidation, right?
Yes,
So
sir.
after oxidation, we go for ion implant. We go for a doping. We don't. So this
Okay.
window that you are seeing is we are not etching the oxygen at this point. We so here in this figure you can't see, but there is an oxygen layer present below the mask between above the silicon surface.
Oh, I understood. Like normally we will be having around 3 nanometer or 4
No, no,
nanometer
no.
oxide layer every
So
time.
the oxide layer that so we don't directly implant on a bare silicon. We do implantation on our oxide. So because what we usually in our wafer what we do is we create trenches. So in our wafer we don't have one device, right? We have multiple devices. So
Yes.
and you can see this is spreading out. So if the if the well if the dopant well of one device is touching another device, then it's a problem. So we want to isolate each and every device. So for that we create a trench of oxide. So between devices there are much deeper oxide layers. There that is some very complicated processes. So my point is when we are doing our iron implantation, there is an oxide layer already grown oxide layer on the surface already. So our iron implants are first going through that oxide and then into the wafer. So so the energy they lose through the oxide will be higher for our n-type dopants. So when they're entering the wafer, they are they already have much lower energy. So hence they are staying near the surface. For p-type dopants, they can penetrate deeper into the surface
Why, sir?
because
Why?
they at because they lost less energy traveling through SiO2.
And why N types? I didn't. I just confused. What?
So your n-type dopants are losing more energy. Your p-type dopants are losing less energy because they are smaller.
Wha- wha- Oh, okay. You are telling P-type
Bo-
dopant. Ah, yeah, certainly. Two,
boron,
three
are,
elements. Yeah,
boron
they
is
are
much
smaller.
smaller than your, even phosphorus or arsenic. Arsenic is much bigger.
Ah, yeah, yeah. I understood now. So since they are bigger, they
They are
can't.
losing much higher, more energy. As they travel down, they are losing more.
Oh, that's why we see them on the surface. But in case of P-type, they go deeper into because
Yes.
of smaller size.
Uh, but sir, mobility is also high in N-type.
Mobility is not mobility is that mobility is of electrons, not of atoms. Here we are diff, diff, here we are using atoms and ions.
Mobility is like whole
Yes.
different concept. It is not somewhere related to.
Mobilities of electrons, the electron mobility. So when they are part of the lattice, when we are giving when we are flowing current through them, their electrons are moving. So in case of in case of p-type, your majority carrier is holes. Holes there we the current is through hole movement. So there we say there we bring the concept of mobility, electron mobility, hole mobility. But first we have to incorporate those atoms into the lattice. So here we are talking just about the lattice. Mobility does not come here.
Mobility plays a role only when you do something measurements and all. Like when you use it for when you apply potential difference, mobility comes into role. Otherwise,
Yes.
I think it won't come.
So any other doubts?
Sir, I just like in the previous class you spoke
Yes.
about wafer. Like I can't imagine like how wafer like there are scribe lines. Why they have drawn the scribe lines I didn't understood, and what they tend to tell by marking that square parts in the wafer.
So this scribe line. So,
These things. Like what scribe lines means and what that die means, and how many transistors are there in a die, why they are separated.
yes.
I just want to know how.
So basically you have one big wafer and your each chip that each device that you are making, that whatever each IC that you want to make, integrated circuit, that that is not. So this is a 300 nanometer wafer. Your 300, sorry, 300 millimeter wafer, but your IC size is not 300 millimeter, right? I, IC is like some
Yes, sir.
micrometers or millimeters. Uh,
Like you are telling, like there are like billions of transistors. There are billions of transistors just
yes,
in
so
a
each chip,
chip.
this is one chip.
When they speak, they will speak only in perspective of chip. They won't
Yes,
speak
so
about
this
wafer.
is chip, one chip. So on a wafer, you make multiple you make multiple IC devices. So you want to utilize your wafer maximum, right? So
Yes,
so
sir.
you divide your wafer into squares. Like right now they're imaginary squares. So so each square is now called a die. So your lithography part your lith so when you are making devices, all of these will be identical. All and each of them
Yes.
has millions and billions of transistors. So
Yes.
after all the fabrication is done, you will cut these wafer into these square pieces.
Okay. Sir, while cutting, they won't
So
cut a
that is why they
transistor
are
in
making
between.
these imaginary lines, right? So that they know they know how much wafer where they will cut the wafer. So they and how much area they will lose in the cutting. So it's not like 100.
Like it's a continuous array, na, sir. While they are
No,
fabricating a
they will
transistor, it will be continuous array. How
no
they can tell that I can
they will
cut
leave
here?
some space, right? They can control the pattern. They can control everything in this, right? So they will they will leave some space on the edges of the die so that when it is cut, there is area remaining for them to the there is they don't and and it's not necessary that they never cut any transistor. They might cut some part of IC in some cases, but mostly they leave some area they leave some area for the wafer cutting. They know where they want to cut the wafer. So while fabrication, they are taking care of that. They are not making.
Sir, when they are doing layering, when they are depositing metal to make connections, they will make connections specific to only one die. For that single die, they will be making connection, and next they will be making connection for the next die. There will be no
No,
connection between the
between
either
dies
dies.
there is no connection, but they all these processes, all this deposition, all this layering, everything is done for everywhere. But using lithography, using the patterning, they are making the devices on every single piece. So at the same time, you are doing process everywhere, but using patterning so that device is not connected to this device. Each of them are individual devices on their own.
Now, what the chip I am
Yes.
having in my device, it is one of these.
So
Okay.
like you are using what some Qualcomm Intel processor in your laptop.
Ah, yes. Normal processor. You take anything, they will be having a processor, small
Yes.
one.
So
That is
they are
one
taking a
of the
300
die.
millimeter wafer. They are making like so each wafer can give them like let's say 100, 500 of these 500 of these chips. Now now there are you can see these are like edge pieces. you can see these are edge pieces which are not complete squares. So they won't have the full circuit that the center one has. So they are useless. Uh, And even the center
Yes.
pieces, not everyone will be perfect. Be perfect. There will be some defect somewhere, which will affect the performance of the final chip. So that is what we call process yield. So how many working devices we are finally getting from a single wafer? Yeah. So this
Okay, sir. I
script line
understood. Thank you.
is denoting where exactly the wafer would be cut, and when the wafer is cut, some portion of the wafer is lost during cutting at the edges. So they take care of everything. Yes, yes,
Sir, hello. Sir, there is a circle type wafer. Okay, sir. And during cutting, there is a many chips which is edge. Okay, sir.
yes,
Not the proper square shape. That is the
yes.
wasted for me. Okay, sir. Then for preventing this type of wastage during cutting, why we are not going for the square shape wafer instead of this
So
circle type
that
wafer?
will,
I would say cutting it is a very difficult task. See, sir has in a one video he has shown like while growing itself, you
yes,
grow it in a rod shape only. So cutting also they will use the similar pattern. They won't grow in a form of box. So if you see Cherolsky process and what
Yes,
it
yes,
gives
I'm
this kind of
yes,
thing.
yes, I'm asking that why we are going circle shape. If there is lots of wastage, then we have to invent the such type of technologies so that we can grow the square shape of the wafer so that we can minimize our
yes. So
wastage part in during the cutting. Means instead of the Jochowski float zone, we can if there is a separate mechanism to build our wafer instead of the circle in square shape. That is the very
see,
good, I think.
see, you are limited by physics. So the so what you want. So when you are growing your wafer, you want everything to be uniform in your wafer. So that usually there are method. It's not like you can't grow a square wafer, but see, ultimately you have some amount of sand and you are converting it into your IC. So your your thinking should be, if I have 1 kilo of sand, how many ICs I can create from that. See, you are thinking that I have this wafer, how many ICs I am creating from one wafer. But if you look into how many ICs I am creating from 1 kg of sand, then your best option would be a spherical wafer, a circular wafer, because these growth methods give the higher yield, the better performance wafers than than any process that will give us a square wafer.
Like another one thing is that growing
Yes,
symmetric crystals
yes,
is a very difficult task. So like getting that square edges will be it is hell lot of difficult.
yes, but there might be processes which can allow you to grow square wafers, but their performance will be poor, and getting same quality in that same quality, same amount will. So if they had such processes, they would prefer to use that only than this. But right now, what technology we have, this is our best option. If you are interested, you can maybe invent some method.
those.
Yes, sir.
Sir, question number one, sir. Once again.
Hello. Yes.
Hello, sir. Sir, you are working on device
Yes, I
fabrication in
work
your
on
institute?
not, but I don't work on silicon devices. I work on 2D materials. So, like,
Like you are fabricating any devices,
yes,
to be
I
specific?
make MOSFETs. So in 2D so here, so let me tell you how a MOSFET works. So if you see your source and drain, they are N type, right? And your this middle part is your P type. So when you apply a volt, when you apply a voltage here on your gate, on a polysilicon gate, so what it does, it changes this P type to N type. Not exactly N type, but it it changes the bands. It reduces the band such that you can have conduction from here to here. So that is what we call on state. And right now you can't you can see you can't have conduction from here to here. So this is called off state, where the resistance is very high, and in on state the resistance is very low. That is how a transistor works. So in 2D material, so here this whole thing is silicon. In 2D material, there is a very thin material or very thin semiconductor, one or two layers, like the thickness would be 1 nanometer or even less. So that itself that itself is your that itself replaces your whole wafer. So the conduction, the on state, off state, everything is through that wafer. So since it's a very thin material, so right now you learned about Moore's law. So as you know, in the current, the Moore's law is slowing down because there's a physical limit to how small you can make your transistor. So now they have gone to new type of structures, vertical structures, but there's a limit. So where, next option is to go to a different material instead of silicon. So that is where 2D materials come in. So that is what my research is. So I make devices, transistors with 2D materials, and then I grow oxide on them. I do deposition, metal deposition for uh, that is what my research is.
What your substrate thickness
So this
normally is?
silicon wafer thickness. So
No, no,
my
sir, yours,
thickness
yours.
would be like 1 or 2 nanometers.
Sir, then how you will dope it? Like I am not understanding how you will dope it. How
Source
you
and
give as a
drain is
source and
not your
drain?
thickness, right? Source and drain is your area, length and breadth. So that you can do. And so 2D materials, you don't use, you don't usually dope them. They are already doped. So they are doped semiconductor, like not doped exactly, but they are they are intrinsically N type or P type.
Like normally silicon also like we have taken here p-type. I'm asking you how you create the
So
source and the
source
drain
and
in
drain,
that
we
small
usually just
thickness.
make the metal contacts. We take a source and drain. So, so there,
I didn't understand. Like your substrate is of p-type, like you have made a 2D material of p-type. Then
so
how you create that
so in
n-types in
2D
those
material,
p
that is the
to be
benefit.
the
In
2D
2D
material?
material, you don't need these source n-type source and drains. So since so here what you are doing, it's a very thick material, right? Your silicon. So when you are giving your gate, you
Yes.
are you are taking out electrons from here. See, you are taking out electrons from here, or you're taking out holes from here. So, but here you can always, but this region will always get back those holes and electrons from the bulk of the material. So, but in
Yes.
2D material, so since it's a limited thickness, 1 or 2 nanometer, so by giving small voltage only, you can completely deplete the carriers from the material. So that way it won't conduct at all. So it's a different concept. It works on a slightly different concept than silicon.
Like sir, normally when we operate the MOSFET, we will be having
Yes.
drain source junction and a gate source junction. But here for silicon gate,
No,
they don't have
they
any
have, right.
connection as per I can see
See,
from this.
this
They
is
don't
N
have any
plus.
connection where they can
Yeah, see, this is N plus. Then
bias
here
the
you have
gate.
your polysilicon, which is very conducting.
Like gate doesn't
No,
have any contact, na sir, metal contact. Like how they will bias the gate then
this
in your
picture,
picture?
I don't know how, but they have a contact on gate. You can, let me show you. Like here you can see they make contacts from gate also. So like here, this, yeah.
Yeah. Here we can see like N plus region is there.
So they have the, in industry they have many optimized processes, many complicated pictures to do this. It's not easy to understand this. These are not very simple pictures. These are very complicated pictures. But they have a contact on gate also.
Like sir, like how long, what is the typical duration you need to think these things and finally end up getting a device? Like what is the duration you think that it
For
might take, considering
for
all the
my research,
experimental mishappenings?
or
Like sir, in general, since you have a
so
working in
you're
the same
talking
field, you might be having some
from a
insights into it.
wafer to a device.
Sir. Like if you if I plan to work on that, like in general, how much time it might take to end up with a
So you
functioning
are
device?
talking about research or making a device in an industry. So research point of
Research
view,
point
there
of view,
is
sir.
no
Research
definite
point of view.
answer. So if you are following some optimized process, you might get your device in days. But in research, we are usually doing new things. So there is no there is when you are doing new things, you need to do some optimization to get what you want. So that can take months, even years.
Like normally who work on this, like how much duration they will take,
See,
sir, in general?
it can it usually takes some months, let's say.
Because Ainu says that it is giving 6 months time to fabricate one and execute that. I was thinking like is 6 months is sufficient or
So,
not?
as you so 6 months, you if you want 6 months is if you have some experience and not experience in what you want to do, but experience in the project you are doing, like you some simulation experience you like or some previous work you are referring to. So it it is possible to do in 6 months. I won't say it's not, but if you are getting too ambitious, then it might not work. I wo- I don't want to discourage you. It's
Okay, sir. Thank you. Thank you for
it
your time.
depends on a lot of factors.
Sir. Like it is still a very new field
So where
for
you are
India as per as
going
concerned.
also the instruments you have there, the yield you get there is also very important.
Like
So in
what
IIT
about
Bombay
Bombay, sir, in your place?
we have most of the tools needed for device fabrication. So depends on the process you want to do.
Sure, sir. Thank you.